and so I'm Jeff Phillips. I'm an instructor for the course. So I'm an associate professor here at the U. I've been here at the faculty for 8 years now, I think. And this is basically the third time I've taught this course. I created it like 4 years ago, but I was gone. I was gone last fall. It used to have a different, so non-permanent numbers name. But it's effectively been the same course now for 4 years. So a couple things we've changed about this course. So this year is that we're changing the prereq structure in the department on like these sorts of classes. And so we're probably this year, since they were just kind of posted online a few weeks ago, we'll probably be a little bit more like loose on these structures than we have been. But we're trying to require both both like CS 3130, the kind of the basic probability, and also the Math 2270, the linear algebra course. In the past semesters, we've kind of said these courses it's recommended to have the background in probability and so linear algebra. We're kind of making that a little bit stronger, I guess 3130 is going to be like a co-rec. So it's the course. How we plan to teach a course is not going to be too different than it was before. But just as a guide, it's helpful to have linear algebra background before we see the linear algebra. I will go through linear algebra very quickly in this course. Like I'll do the whole semester in 3 lectures, but then we'll move on to some more advanced stuff, and it's helpful to have seen it before. And similar with probability, although that seems to have been less of a kind of the student recommendation was like less stressed. So on the other side of this, they're the advanced sort of data analysis course, like machine learning and like the data mining course that I teach that I'll be teaching in the spring. These courses are going to start to require this course. And so the reason I created this course starting about 4 years ago was that not all students, but a lot of the undergrads going through to take those courses were having some trouble with the mathematical aspects of it. And so this course is meant to kind of to try and like fill the gap between the probability courses and linear algebra courses, and then how they're used in machine learning and in like data mining. All right, so that's kind of the where this course is situated. Yeah.
For those other courses like machine learning and artificial intelligence, will they become more mathematically involved?
They're already pretty mathematically involved. So we're not planning to make them any more. We kind of designed those courses, and we like how we teach them, and that they're very formal. As things are changing, kind of the core elements we're teaching are the same, where packages and so forth are like evolving. But they're fairly mathematically involved courses. So, and that was one aspect that CS students were having trouble with. They could often do the programming part fine, but kind of understanding kind of how to apply these mathematical concepts was something that was coming very quickly. Right? So this class is meant to be in between. You're going to get a taste of a lot of the kind of the coolest stuff that's covered in the courses for data mining and like machine learning, but you're not going to get the most advanced stuff. You're not going to get the breadth. Okay, so you're going to get introduction to things like linear regression, gradient descent, like dimensionality reduction, clustering, and so classification. And I'm going to teach this at a pace which should be much closer to like 3130 and 2270 than these upper level classes. Yeah.
Is taking this course and like upper level 5,000 data mining, machine learning classes, is that redundant, or is this like
there's going to be a couple lectures redundant probably. So like what I cover in like clustering in this class will cover in half a lecture, which is like 3 lectures here will be like half a lecture in the data mining class. The stuff on like dimensional reduction, I'll spend like 4 lectures here. That'll be 1 lecture in the data mining class. Right? So there'll be some redundance, but not too much, and we find that students appreciate to see these things more than once. So it's like this is meant as like we've been working on trying to design this pipeline for all these students who want to take things like machine learning. How do we get you to machine learning so you can take what is really a state-of-the-art machine learning class, the way it's taught all the top universities in the country, how you can get to that and be very comfortable at the point you're in there and do really well, right? So that's what this class is for. Is for. There's what this class is not about. Is it's not about how to do all the programming sort of data processing associated with like like being a data scientist. So this is more focused on the mathematical side of it. You'll see more of that in the advanced classes. And there's another class which we'll teach for the first time in the spring called, so that will be called data wrangling. And it will be called that and get a course number assuming we finish some paperwork this week. But it'll be taught for the first time in the spring, and that'll be more, again, a very kind of introductory sort of like slower paced class, but all about kind of how to quickly gather and scrape data and process it and get it into the right format in Python so you can really easily apply the advanced techniques. Okay, so these are the 2 courses we've added from a traditional CS courses that are going to get you ready for these advanced courses for like doing stuff in data science. All right, so that's kind of a high level. The plan for today is to kind of just go through the operations of the course, and then I'll try and kind of, I've said like things like clustering, but I haven't told you really what clustering is, and so I'll try and give you kind of an overview lecture of the entire class, kind of in the kind of the second half of like this lecture. So the kind of the main programming language in this class is going to be Python. By programming language in a CS class, we aren't going to spend a ton of time on Python. Just pretty much sometimes I will show you some examples. I might ask you to do some really simple stuff in the homework. But the plan is not to teach you Python. The plan is hopefully you can kind of pick up the basics kind of as you go. How many people have used Python before? How many people have not used it? Okay, actually, so last time I taught this 2 years ago, that was different. So I assume what I plan to cover at least will be super easy for you guys. So I might try and ramp that up a little bit. The other thing we're planning to do with that is there are 2 TAs for the course. So they're right down here in front. So there's a lock and there's Ben Wade. Do you guys want to raise your hand? Yeah, so they're planning to have, so the couple things they're going to do, they're both kind of very well versed in this material. So Ben Wei actually took the course 2 or 3 years ago. So he's now a PhD student. So they should be very knowledgeable in this. They're going to hold office hours. We've posted some possible office hours for them. And the other thing, I'm going to ask them to do some like some like basic like tutorials in Python. we're not so much going to cover, like I said, much Python in class, but they'll do maybe 3 to 4 of these tutorials at some point outside the regular class time probably, where they'll just go through some extended examples, setting stuff up, and like the first one would be like doing stuff in like a Jupyter notebook and so forth. Just to help you get up to speed if you haven't seen this before. Python is kind of becoming the language that a lot of data science is used most commonly in. And it's not something that we really teach in any classes so much. The algorithms and the mathematics is not specific to the language, but it's easy to do a lot of the stuff that we'll do in Python, and it's usually as efficient as anything else. Occasionally, I found in my experience I need to drop down to C to do something because Python just doesn't have like sparse arrays implemented in a way that's efficient enough. But usually Python is efficient, and a lot of the stuff is built in. So you'll find a lot of the stuff we'll talk about in the class are the most basic option of what is built into Python, but we'll explain to you why it's doing it that way, and what's actually going on, and how to think about it, and how to get it ready to call that function and to use it in a way that's actually useful. Okay, so the other thing I'll mention about the office hours, I'm planning to have office hours an hour from 10:30 to 11 on Thursday morning, and then I'll try and be available for an extended period of time after the class every Monday and Wednesday. And then these are posted times for Benway and Alak. And so if you look at these times, you're like, I have class every single one of those times, please let us know now. If we don't hear anything, then we'll book rooms for them, and those will kind of be our default office hours. But if there's a major conflict, please let us know, and we can rearrange stuff. It'll be easier to do it now than later in the semester when you're like, oh, I need help, and now I realize all the office hours are during times I'm not able to go. All right, so if I don't hear anything, then once I post an actual room on there, then that means they're probably kind of official. We can still change them, and please let me know if things aren't working out or there aren't enough office hours at a certain time. So just let me know, and we can change stuff. Okay, so the book for the class, there's a link to a book here. If you click on it, it'll bring you to this page. This is still on my webpage. And the book is linked off of here. It's in a PDF, and like if you want, you can download it. This is a book I've been writing. I printed it off for the first time, and it's like 200 pages. Hopefully, it'll be printed within like the next year. It'll be published, but for now, and it's available online for free. This book started as the course notes from this class, and then I added about twice as much other stuff, right? So there's about 200 pages in here, and we'll cover roughly 100 of those pages, and probably the easiest 100 pages in those books. So there's more complicated stuff that'll come kind of in the back, and we won't go through even in chapter 2, we probably won't go through all of chapter 2, right? So we probably won't talk about all this stuff in sampling unless we end up going fast and you guys, and we have time to hear about that sort of stuff. And we will skip chapter 4, and some of this will go into my data mining class in the spring as well. Hopefully there's examples. Hopefully there are useful examples to kind of figure out stuff and explanations and pictures and stuff. So I hope you appreciate the book. I wrote this because there wasn't really a coherent set of material about this class online anywhere, so I ended up, making this with myself. It's not finished yet, okay? I'd say it's more than 90% finished, okay? But there could be typos, there could be mistakes, but like hopefully not too many. If you find them, please let me know. I'll be very appreciative if you find some. But the actual material that we're going to be covering in the book is probably more solid and has been used. This will be the 4th semester effectively it's been used, so hopefully it's in pretty good shape. Okay. One other thing about how the class will operate, I'll do most of the communication through Python. Through Canvas, right? So I'll send out announcements through Canvas. We'll have we'll use the Canvas discussion boards. The TAs will be on there, and I'll be on there to answer questions. If you have a general question about the class or the homework, the right place to discuss it will be on the Canvas discussion boards. I'm usually pretty good about responding to stuff. Don't post things like, oh, is this the right answer to homework question 2? If you do that, I will take down the post, and if you do that more than once, you'll start to get in trouble. If it happens once, it's a mistake, it's okay, but try not to do that. Otherwise, almost everything should go on the discussion boards for Canvas. Okay? You can talk to me on my office hours, and if there's something personal, you can contact me directly, but it's more efficient to use the discussion boards on Canvas. And I'll post announcements through there, so just make sure you can get announcements and email on Canvas. The homeworks will also be turned in on Canvas. We're still debating whether, in the past, I've only allowed homeworks turned in as like a PDF, which usually is not a problem. You make in something and you can print it out to a PDF, and then you can submit it that way. That ensures that the way we see it is the way that you see it, and then you're responsible for how it looks because it looks the same in our computer. We're toying with the idea of turning in like an IPython notebook instead. Most of the stuff I'll be asking you to do will be more problem setting. There'll be some stuff I'll ask you to run some stuff in Python, but that should be simple, and you can just print out the answers. But the plan right now is probably to turn everything in PDFs. That might change. It'll be on Canvas. They should be loaded in there with dates. So you should be able to see the dates in there. And then, so the way the grading will work in this class is there are going to be 5 homeworks and 4 quizzes, and then there's going to be a final exam. And the final exam will be worth 20% of your grade, and the homeworks and quizzes will be worth 80%. And there'll be 9 of them, and you'll get to drop the lowest one. Okay? So if something happens and you can't do a homework because you're super busy, or you miss one of the quizzes, that's okay. You can drop that one. Okay? And so that means the ones you don't drop are each going to be worth 10% of your grade.
Are the quizzes in class, or are they like on campus?
Yeah. So the quizzes will be in class, right? When I have a quiz, we'll still have a lecture, and then the last, I think, half an hour of the class we'll have the quiz. That's generally how I plan to do it. Hopefully the quizzes are easy. I assume some people will finish them in like 5 minutes, but I'll give you 30 minutes just so time should not be an issue. Right. So it's meant to be kind of checkpoints, so you're forced to study, which makes you learn better. Right? That's the reason.
Is the final in class?
What?
Is the final in class?
Yeah, it'll be just like regular final. It'll be in this room. I believe that's the date. I looked at the calendar, December 12th on a Tuesday, 3:30 to 5:30. Right. So it's on the regular exam date. So it's not the last day.
You said that the homework has to be turned in a PDF form. Does that mean that we have to use LaTeX, or can it be like handwritten as well?
You know, I generally like LaTeX because then you can format stuff just the way it's supposed to be, and it's clear. It's a nice tool to use. I use it all the time. I know probably in some jobs you'll probably not ever use LaTeX. So I'm fine if you handwrite it and say take a picture with your phone, and if that looks good and it's legible, that's fine, right? If it's not legible, if you take it at a weird angle or something like that and we can't read it, then that's your fault and you might lose points for that. Okay, but as long as it's a PDF and it answers the questions clearly, it's fine. You know, the easier it is for the TAs to read, probably the more generous they'll be, right? So, you know, so but you all need to decide, you know, that trade-off for yourself. Yeah.
So it says Tuesday, 12/12, but Tuesday is the 10th. December. So is it going to be on Thursday or Tuesday?
I will check. Yeah. So thanks for pointing that out. I'm not sure. I copied it from someplace and I missed one of those things. Okay, good. I'll fix it. It'll be up to date. We've got like 3 months, 3 or 4 months to figure it out. So hopefully you can plan around that. I should mention the dates of the quizzes and the homeworks are not completely set in stone right now. I might move them if there's, I don't know, like a snow day or something and the schedule gets off. Then we can change stuff, or if we're falling behind or moving ahead, we can try and change stuff a little bit. I'm generally tried to have the quizzes and homeworks on most homeworks are due on Wednesday, except for this one. I wanted to have before quiz 2, and I want to have the quiz on the day before fall break, so you don't take it right after fall break, which I think would not be as good. And then you don't have anything to worry about over fall break, which is
That's
at
nice.
least from this class, so
That's
that
nice
should
of
be
you.
good. So we try to put more office hours, I think, earlier in the week. But the homeworks each should be out for like 2 weeks at a time, and you should probably be able to do most of them at the time we put them out. The quizzes, there aren't the same number of quizzes and homeworks. That doesn't mean that quiz 1 is exactly on what was covered in homework 1. It'll be roughly on what we've covered up to that point. It should be, if you're coming to class and paying attention, you should be able to, and asking questions if you're confused about something, you should be able to kind of do well on the quiz. Okay? If you're not coming to class, or you're coming to class and you're not paying attention, then you might not do well. I hope you come to class and pay attention. There's a really clear correlation between the students who come to class and pay attention and the ones who do well in the course. That's the #1 advice I can give you. I understand that you all have lives and constraints, but you should try and come to class and so pay attention. So one thing I'm test driving, trying to do, is to try and record this class. I've done this for my graduate level classes for a while, and a lot of like the machine learning and visualization and algorithms classes are also often recorded. And so I think we're going to try and do it for this class. One advantage of this is that a lot of students will go back and rewatch the lectures for parts that they may have missed. Disadvantage is people are less likely to come to actual class. And now I think that's probably fine if you're always watching the videos basically roughly on the same day. The way this will work is it's being live streamed right now so it's being live streamed on YouTube, and it will basically be available within an hour from when we end the live stream. Sometimes it's available, like it's immediately available. Sometimes they process stuff for like 45 minutes. Okay, so it should be available online. You should, something might happen. We might miss a lecture, but we've got a system we've been working on it's pretty full, not foolproof, but kind of 90% of the time it works without any hitches. So, which means many more than 90% of the lectures are online very easily. So you can plan your schedule around it. You can live stream and ask the questions to the TAs, and they can ask them to me and so forth. But it's a little bit better to be interactive. I'm planned to do the course mainly on the board. Okay, and I'm not quite sure how it will work. I've done before where I've written on an iPad on a big monitor, and that works pretty well. We'll have to see how this works. So don't quite trust it yet, and I'm not sure we'll do it. But we'll have to see how the first few of the lectures. So it should be, there should be a lot of material easy to keep up. The book will follow the lecture fairly closely, at least the chapters we will cover. The lectures hopefully are going to be online, and you have class, right? And we'll cover it in class, and the stuff you will be tested on is what we're covered in class, right? So you'll have kind of several resources to learn about, to ways to learn this from, and hopefully it will be material at a pace that is, is something you should all be all of you should be comfortable with the pace of it, hopefully. Okay. So grading. Okay. So the late policy on the homeworks is going to be every homework will be due at class starts at 3. The homework will be due at 2:45. Okay. The Canvas due date might be slightly later than 2:45. If it's marked late on Canvas, it's late. Okay, officially it's due 2:45. If Canvas has a later date, that's a grace period. After that is not a grace period. Okay, you can turn it in. If you turn in 0 or 0.01 to 24 hours late, you get 10% off. That's 1% of the overall grade, and up to 48 hours late, you can lose up to 20%. After that, I won't accept anymore. Okay. And you've got a one you can drop, so it should be flexible enough in case you have something come up. If there's a medical emergency or something like that, that's I'll take doctor's notes and so forth. But otherwise, it should be flexible for most of the normal stuff that happens in life, and you get delays, and hopefully it just averages out. And then so we're in the school of computing. There's a standard academic misconduct policy. You should read this. You should try and follow the policy of similar other classes. You can talk and kind of work through stuff on your homeworks, but you should write everything up yourself. You will learn better if you do this, so don't rely too much on working with people. You should try and figure stuff out yourself. If you can't figure out yourself, you ask me or the TAs, and we'll help you figure out. This is the stuff that you need to learn, right? That's why we're asking you for homework questions about it. Okay, and then on the quizzes, I have a strict no talking policy. So during the quizzes, you can raise your hand, and then me or the TAs can come around. But if you're talking otherwise, I will assume you're cheating, and you'll get a 0 on the test. Okay? So that's just the policy. I think that's reasonable. Okay, and let's see. And that holds for the final as well.
Hey, Jeff, I got one quick question about this academic conduct policy.
Yeah.
At the beginning of every class, every year, all professors, give us the spiel about the academic misconduct. You're referring to an acknowledgement form here which we signed like a very first semester, first class.
Yeah, that's,
So it
yes,
should
same
already,
one.
we don't have to do that again specifically for this class.
Yes, that's right.
Okay, so
That's
as
right.
long
There's
as
one
the office has it, we're good.
Yeah, as long as it's on file, just kind of you're acknowledging this contract to get into.
I just want to make sure we never like
Yeah.
redo some.
No, just once. This is kind of,
Standard spiel. Thank you.
yeah, that's right. Right, so we have these policies because unfortunately, people cheat on stuff, and if we don't enforce them, then people will cheat and get away with it, and they won't learn, and we won't be teaching them properly, and they won't be fairly representing who has done, who's done well and who hasn't done well. So unfortunately, we need to have these policies in this discussion. If you do cheat, we likely will catch you, and it will not end well. I don't recommend it. Okay. Okay, and there's a few more stuff in the actual syllabus document up here. Kind of rough things about grading, basically on the standard letter scale, late policy, collaboration policy, cheating. If you need, if you have disabilities or you need extra help with something, feel free to ask. This is perfectly happens every semester. It's better to check with me at the beginning. Kind of safety and like sexual misconduct. If you see something inappropriate, you should report it. There's a bunch of information here. If you're just concerned about something, go here. The university is trying to put a lot more resources into these sources, and they're like non-judgmental. So feel free, if you're not sure, just call, and you can. It's better to do that than to not call and then to which you have it. So okay, and then if I have two Highleys here. I probably don't need the two Highleys, but I generally recommend LaTeX for my homeworks. If you want some place to get started, I've got some sample documents here, and probably in the tutorial there's I guess there's one of these Python notebooky things that you can do LaTeX directly inside there now. So it's got even easier. You don't necessarily need to worry about having a separate program for that in the way you have in the past. Things like Overleaf, which has its issues, but have made this much easier. So okay, I think that's pretty much the kind of the basic ins and outs of the course. The schedules up here will pretty much follow the schedule. These are actually links, but I don't think I don't link to anything right now. I don't have the chapters of the book kind of as separate files currently. If you think that will really help a lot, I can. If you want, I can do that. But I don't have separate links for them. But I tell you what chapters we'll usually be going through. Right? So it's like 2 parts of a chapter in one day. You'll look at them, they're like 2 or 3 pages. We'll cover them at a pretty, at a very reasonable pace. So as I mentioned, the point where that's not quite, well, I think it's still reasonable, but where it's a little bit different is the first 2 lectures starting on Wednesday on probability review, and then the linear algebra review will have 3 lectures, and these will be a faster pace. Okay, I kind of expect you to know this before. They're kind of prereqs or coreqs, but I'm going to go through them anyways because we're going to really need probability and linear algebra to understand everything else in this course. So I will go through that quickly. Basically, I will do 80% of 3130 in like 2 lectures. Okay, just to kind of remind you of notation, review the most important stuff. Then we'll dwell a little bit longer on Bayes' rule and doing Bayesian reasoning for thinking about data. Okay, this I think is usually covered in 3130 or the equivalent in the math department. So we'll kind of go at our usual pace when we go over Bayes' rule. because this turns out is pretty important for thinking about data. Okay, and then this is another kind of probability section, and it's related to the central limit theorem, which, who's heard of the central limit theorem? I guess that was in 3130, right? And it's in a bunch of math classes. If you haven't heard of it, that's okay. If you learn this in the math department or in a statistics statistics class, the basic point of the theorem, which is actually kind of a few dozen related theorems, is basically the same, but we use it very differently than a statistician would use it. And so I will present it from a way a computer scientist can use it. Saying central limit theorem is basically, the way I think about it is as you get more and more data, you get a more and more accurate answer. Okay? And we're going to talk about how to say, okay, how much data do I need to get so accurate of like an answer? If I want this accurate of an answer, how much data do I need? If I have this much data, how accurate is my answer? Okay, and in ways that are actually quantifiable. You can write down, do a little bit of algebra, and you get an answer. Whereas in a statistician, they'll say, as you keep getting more and more data, it gets better, right? And here's kind of how nicely the data has to look. We'll try and say, we can assume fairly nice things about the data and then write something very specific. Anyways, we'll spend 2 lectures on it. Don't have to worry about all that now, but this is kind of the language that is used to describe how accurate data analysis algorithms are. Okay, they require probability because there's a lot of uncertainty in the data you have. Okay, I don't know if I have all the data that's out there, right? There's uncertainty in the actual kind of how trustworthy the data is in a lot of ways, and you need the language of probability to describe this, right? So it's not gonna, we're gonna describe algorithms in this class, and they're gonna be cool in that they're not gonna be like an algorithm for like sorting, where you have an input and there's exactly one right output, but you're gonna have some input and you're gonna come to some sort of output, which is going to be a model. And there are lots of reasonably good models, and you're gonna find one of them, and maybe the more data you have or the longer you run it, the more accurate it is. Okay, but there's not like a fixed output like sorting where you know you can check is correct. And so you need a different language to describe this. Right? And so this will give us some of that language. Okay? So that's why we need all this probability, in order to describe this language of this type of these algorithms. Okay. And then we need linear algebra. Okay, the reason we need linear algebra is because often data is represented in vectors and matrices. Okay, and linear algebra is the language of vectors and matrices. So to describe the algorithms, you need to describe them. The input is a data that, the input is a vector, the input is a matrix, the model is a vector, and so forth. And so we need linear algebra to describe kind of these algorithms. And then about halfway through the semester, we can start getting into actual techniques. Okay, we'll talk about so linear regression. This is a simple technique. I'll kind of go through. I'll quickly go through this. I'll go kind of give examples on the board. And gradient descent is thrown in here, and I'll explain why that is. And then PCA is all about high-dimensional data you're reducing down. This is a lot of linear algebra, clustering, and classification. Yeah. So let me try and explain these on the board. Okay. So probably most of you have heard of linear regression before, and maybe you've even applied various parts of it, but you're going to have some, so I'll try and do this in picture form. because we don't have the mathematical notation yet. Okay, so one of the things in this class, this is going to be kind of it's a mathematical class, and that means there's going to be notation, mathematical notation. Some of it you probably haven't seen before. I'll try and explain it as I write it, and that's part of what you're learning, right? So if I haven't explained something or you don't know what a symbol means, please stop and ask, okay? But I'll try and do stuff today with just pictures, and then we'll get through we'll build up the notation as we go. Okay, so linear regression, you think of having some data points, which are now here these black data points, and so you can think of these as having an x-axis and some y-axis, okay? And you could, for instance, let's say this is this, for instance, could be the height of a population. Could be people. So it could be like elephants, and then this would be the weight. Okay, and so every data point has its height value and its weight value. Okay, and the goal is to build some model, which is a rule, all right, which is going to look it's going to look something like this. It's going to be a line. So linear regression, for now you can think of it as a line. Linear will take a different meaning so later on in the class. And the point of this line is that the data is supposed to be close to the line. And it should be close in the sense that in this vertical distance, it's close. I don't want these green lines to be very long. Okay, and then technically we won't want the sum of the squared lengths of the green lines, but we'll work through that. But more importantly, it's going to be a model, which means I'm going to get a new data point potentially here where I only have the height. And what this allows me to do is to make a prediction of what the weight is going to be. Right? So when I get a new data point for the height, I need to predict what the weight is, and so I go up to the line, and whatever the y value of the line is my prediction of the weight.
So Jeff, are we going to have that model expressed as an equation of some sort?
Yeah, we'll express it as an equation.
Plug in the height, you get the weight.
Yeah, you can write down an equation. What will be better is that you can describe this just as okay, so there'll be two secrets of this class, and the first one is that data points are vectors, okay? And so each data point we'll describe as a vector, and so a data set might be a matrix, so it'll be a stacking of vectors. And two, that models are also vectors. Okay, so if I write this down as an equation, you won't immediately see that the model is a vector. Okay, but and this is not just linear models. All sorts of models will be vectors, or maybe they'll be matrices as well in some cases. But the models will also be vectors, and that's a more general way of thinking about it. If you just think about it in this two-dimensional picture, yeah, I can write down this equation where I say that y hat equals ax plus b, right, where b is this offset, and a has to do with the slope here, right? So I plug in x, and the x value, I multiply it by a, I add b to it, and I get some prediction. I can do that, but it will be more natural and more general to higher dimensions when I have not just one value I'm using to make a prediction, but I have a set of values I'm making a prediction. I'm going to want to write down the whole model as a vector. I'm not going to want to have a separate part A here, and then I add a B. I'm going to incorporate these all into the same vector. This will just be more natural and more simple once you get used to that. Yeah.
When you say model, are you referring to the blue line, like the?
Yeah,
Oh,
right. This blue line is a model, right? It's not, the output of our algorithm here is going to be a model which is just going to be represented as a vector. You're a computer scientist, that means it's going to be just stored inside an array, right? A vector is an array. But there's an interpretation of it, a nice interpretation of this line, right? And in the simple case, the line is described by this equation. Okay, so we'll work through this mapping. I don't want to do it all now. We'll do this. We'll build this up in a way that's proper, and this will generalize not just to linear regression, but we'll look at other things where maybe I don't want it to be a line, but I think the model is going to be better if it's going to be some curve like this instead, right? So I want to describe it as a polynomial curve. This probably isn't the right polynomial curve, but let's say this was a good polynomial curve. I can fit that model. It uses, I also represent as a vector. It's going to be a different vector. It's going to be a larger vector, it turns out. But I use the same machinery to calculate as I did with the line. Okay, if I have higher dimensions, it'll also be a vector, just a higher dimensional vector. Okay, so that's why we're going to need all this mathematics. Okay, so we talk about ways that you can see the simple thing you may have seen before, but we'll see it more like in more general. Okay, so this is linear regression. Okay, so we'll do within here. Okay, one issue you get to with using a polynomial model is then I can fit some crazy model here that goes through every one of the, not quite like that, but it can go through every one of these data points. Okay, I can fit a polynomial that does this. This is not a very good model. I'm still making the prediction in the same way. It turns out it's roughly the same prediction, but sometimes it kind of goes kind of wildly up and down, and probably that's not what's actually going on. So how do we choose the right level of complicatedness of the model? We want to trade off making all these these vertical lines small versus having a simple model. We'll talk about cross-validation and overfitting here, which is a super important concept, which is like if you take a class in statistics, I guess Math 3080, I guess is with hypothesis testing, they give you a completely different view of how to kind of make judgments about data. How well is something working? Cross-validation is a big data view of the world, and that we can use data to choose the model instead of choosing a model and then evaluating that in some specific way. So it's a much more flexible way that allows you to choose the right degree of complicatedness of the model. Okay, so then we'll get into gradient descent. And so it turns out for linear regression and polynomial regression and higher dimensional versions, there's a closed form solution with linear algebra. You can write one line of matrix multiplication and inverses and so forth, and it will give you the optimal solution. Okay, but that's not what people use in practice. It turns out to be kind of slow, and although it's kind of optimal up to the numerical precision issues, you don't need all that accuracy. Instead, people use a gradient descent view of the world, where it takes advantage that models are vectors. And so now we can think of, we're going to search over the space of all vectors to find the best model. Okay, so instead of writing an algorithm that executes kind of a fixed set of operations, I mean, it's still kind of doing that, but it's going to kind of start with some guess of what the right model is and kind of walk in a way that keeps improving. Who's seen gradient descent in some form before? Okay. So, but others of you have not seen this before. It's it's like how most of these algorithms are actually run is with gradient descent. We'll start with this because it's going to have a more traditional closed form. You write a line of linear algebra code, and poof, out pops the right answer. But most of the time, for scalability reasons and flexibility reasons that we won't entirely get to, gradient descent is going to be the tool of choice. And it's going to give you a slightly less accurate answer, but it's going to be much more flexible. Okay, and this will be a sort of algorithm that the longer you run it, the closer it gets to the right answer. But it will probably never get to quite the right answer. Okay, so after that, we'll move on to PCA and like dimensionality reduction, and we will center this around discussion of the singular value decomposition as the primary kind of tool for doing dimensional reduction. There are other ways too, but we'll focus on the ones with singular value decomposition. Who's seen the singular value decomposition before? Is this taught in the linear algebra course? Yeah? Or is it? I've heard sometimes it's taught and sometimes it's not taught. So if it's not, that's fine. We'll cover it here. And if you've seen it before, I'll probably explain it in a way that's probably different than the way they explain it. It might end up being the same, but there are lots of ways to think about it, and I have a kind of a data-centric way. And what this will be about is, okay, here we had data that was kind of one or is two-dimensional. We're now going to think of data which is in some, there are lots of these different axes. I can't draw on the board. There's two I can draw. There's a third one you can kind of think of coming out of the board. And then there are also these other ones which I can't draw. And we'll use linear algebra to think about these high-dimensional concepts. So this will be more natural at that point. But you're going to have these points which live in this high-dimensional space. And the goal is going to be to find a low-dimensional subspace. Let's say we started in 10 dimensions, and we're going to go down to this 2-dimensional subspace here. And the goal, again, is going to be so that the distance, if I project all these data points onto this subspace, that the length of these projections is going to be as small as possible. Okay? And the idea is that, okay, if my data is really high dimensional, I might not need all of those dimensions, right? I've kept a bunch of kind of attributes of some customers for the company I'm working with. And I think I don't need all of those. Some of them might be redundant. There are some that are just, they don't vary a lot from customer to customer. I'm going to kind of figure out how to kind of throw those away. Now, what we'll talk about won't really throw them away. I'll kind of blend them together in some way, and we'll talk about this. So it'll be helping you think about what is data in high-dimensional kind of, how's the data look like? With the linear regression stuff and gradient descent, everything you can think of in 2D, and you can basically get all the concepts pretty much. There's a little linear algebra you need, and that just will magically generalize without much thought. But here we'll need to, with dimensionality reduction, we'll need to think about high dimensions. So I'm a very geometric person how I think, so I'll try and draw lots of pictures, and I'll stretch those as far as I can into high dimensions I can, but the natural way to do this will be, again, with linear algebra, will be essentially. Yeah.
And the acronym PCA stands for?
Principal component analysis. Yeah. We'll see that. Yeah. Okay, so if you've heard of eigenvalues, hopefully the linear algebra class taught eigenvalues. Okay, so eigenvalues turned out are very closely related to all of this stuff as well. It's kind of a twist on the transformation. Okay, and then we'll talk about the power method, which is a simple method to actually calculate these things. And we'll find out that when we did linear regression and there was a closed form solution, you typed in some linear algebra, you were actually running one of these algorithms, and we'll see that it's actually not as closed form as you might have thought. That is actually, again, an iterative algorithm, which the longer you run it gets closer to the right solution, but never really gets there. But it gets there very quickly, right? So
That's the clustering.
that's the power method, which is in PC. So we'll actually show you one way how to calculate all these things. Although, you don't have to do this yourself. It's built into all these packages, and it has been for like 40 years. But I think it's illustrative to kind of just see how it works. It's like 3 lines. So okay, most of the algorithms are like 3 or 4 lines, but they just take you a lot of kind of conceptualizing to like get what's going on. Okay, and and then that's just some kind of extensions we'll do, and then we'll get into clustering. Okay, good. Okay, so one more panel here. Okay, so what is clustering? Clustering is a different problem than these two, in that you're going to think about data points, and at a very high level, it'll be useful to think in just 2-dimensional data again. This will be fine. And I'll be given data that looks nice and 2-dimensional. These dots are too small for you to see them. Make them bigger. Okay. Okay, and when you see the dots, the data points on the board like this, what's your first thought? That there are 3 groups of them, right? So here, here, and here, and these would be called clusters. Okay, so basically clustering is you have data and you have groups of points which you want to kind of say these should be somehow related to each other, but not related to these other set, which are internally related to each other, and similar, this is a third set, not related to the first 2, but internally they're all close to each other. Okay, and we want to automatically group them in like in this. Okay, this is we will talk about the kind of the most common way of doing this, which is the k-means, so formulation of clustering. We'll walk through this. We'll have a little diversion into these Voronoi diagrams, which will explain a little the geometry of clustering and about why this is harder in so high dimension. In low dimensions, it turns out there's a lot of easy things you can do. In high dimensions, things get tricky. But there's a very simple algorithm that will walk through the standard algorithm that everyone uses that makes it easy through linear algebra again, even in high dimensions. And then we'll extend this to using EM and mixture of Gaussians in a way so you're not just finding these clusters, but you're also doing something more interesting. You're finding, kind of for each cluster, you're saying, here's a mean, and here's like a standard deviation. So you're actually fitting a model on top of each of these clusters. Okay? And this will map back to stuff that we do in a couple weeks from now with the Bayesian perspective on data analysis, and that will basically be saying, we're actually able to fit a model saying the data came from this model. And this is the best fit model onto the data. And it turns out it'll be 3, in this case there are 3 kind of Gaussians that fit here. It's a technique called mixture of Gaussians. And it'll be a direct, simple extension of the k-means technique, as long as you understand the basic probability. It's not very hard to get to this instead, but this is much more powerful. Okay. Okay, so it'll be, with the case of linear regression axes are somehow direct extensions of these approaches. With clustering, it's a much broader area, and there are lots and lots of formulations of clustering. And so again, the k-means and the mixture of Gaussians are probably the most popular of these, but maybe that covers 40 to 50%. So there's much more going on there. On the other hand, clustering is a thing where it kind of either works or it doesn't. And like, if your data is in 2D, my actual recommendation is to plot the data and draw circles. Okay? But in high dimensions, this will work. But if you can either reduce the dimensions to 2 dimensions, and that is effective, or it's only 2 dimensions, and then you just plot and draw circles. There's some cases where it goes beyond that, and we'll talk about some of these issues. Okay, and if you want to completely automate it, then here's a way to completely automate it inside the system. Okay, so then the last section will be classification, and yeah, okay, so this is what we'll go to. Let me just, or should I write? I'll pull that up. With classification, we're going to have a slightly different input than before. It can still be data points which are in high dimensions, but the difference is that they're going to be labeled in a certain way. Right, so I'm going to have pluses and minuses. I'll draw circles around the minuses here. And the goal is, again, to build some model. Right? Here the model was the line, or maybe this curve. Here the model was this low-dimensional subspace. Here was either the centers of the groups or a Gaussian distribution on top of them. In this case, the model is going to be a linear separator between the data. Okay? And again, the goal is going to be, in this case, like in regression, the reason I want to model is so that if I have a new data point that I don't know if it's a plus data point or a minus data point, I have a new point here, I want to predict, is this going to be a plus or a minus? If it's over here, it's probably going to be a minus. If it's over here, probably going to be a plus. Here, I might not be so sure, but with this line, I can say, oh, it's on the same side as the minuses. I'll label it as a minus. Okay? Yeah, so this is, I would say, probably the most powerful kind of technique out of the 4 main things I've covered here that has had the most impact of the last 10 years. This kind of data science kind of revolution that's been going on, because we've gotten very good at this. We've gotten data that's come in, and we've had some that's been labeled as good or bad, or these are going to make money, these are going to lose money. This is someone's going to buy this product, they're not going to buy this product, and predicting this, building these models that predicts this. And this is very powerful in lots and lots of ways. Yeah.
But there's no new math here, right? I mean, the math that we use to come up with the classification that you just drew, there's no new math, right? This is all existing math. We're just using it in a different way now. I mean, as it relates to data science.
It's like, what is new math? So,
like new theorems,
new theorems, yeah. People are, what we're covering in this class, the perceptron algorithm, was developed at least in this, it was known at least in the 60s.
In the 60s,
okay. Kernels, okay, so linear prediction is kind of, as a model, that, I mean, I guess people may not realize that's what the perceptron is doing, but the linear prediction maybe came earlier, maybe came later somehow. Okay, kernels and SVMs, they really understood the math in the late 90s, early 2000s. So 20 years. For me, this is still new. All you guys might think 20 years ago, oh gosh, right? That was a long time ago. You know,
Not that long ago.
You know, but for me, this is still fairly new. Neural nets, you know, the perceptron algorithm was initially for neural nets. We'll talk about not just neural nets, but like a potpourri of things, and we'll see how deep and how much time we have here to go into this. But on the other hand, there's lots of new stuff happening every day. There are 20 usefully new papers every day. The big conferences in machine learning this year have hundreds of papers.
Sure,
Yeah, and these are all kind of really, and they're very competitive to get a paper. Each one is individually pushing for the state art various ways. There's a lot of new stuff going on. What are we learning? And this class is not about like new cutting edge stuff. It's to get you so you will be able to understand what's going on in the new stuff, right? And when the machine learning and data mining classes that come after this, there we try and stay a bit closer to the cutting edge. Okay, in those classes, yeah. Mathematics, okay, so again, mathematics is, we mentioned, kind of old, not as old as calculus, right? But you know, hopefully for you, it's not about the age of the mathematics. It's about finding the proper, concise way to clearly understand what's going on. Okay, and so that's the point of the mathematics, is to make it so you can understand and follow these more advanced things, right? And so it's not just, okay, I opened this library, they have 20 options of learning algorithms, and I'll pick one at random because the name sounds cool, right? You want to understand why this one is better than this one. I ran this one, it didn't work so well, and maybe I can look at why, and then using that insight to pick another one that will work well. Sometimes you kind of have to do that. You have to play with stuff to see why, but this will help guide you towards that. If you think, well, this one didn't work well and this one did, you might say, because they both work so badly, I'm probably going to be kind of hopeless on this, and explain why. And then this is stuff that you'll build towards, and I'm getting you ready to succeed in the machine learning class where you will learn that very well. Okay? Okay, so the linear prediction and then the perceptron algorithm is, again, this dirt simple, like 3 lines of code algorithm which can solve this problem. And again, this model here is a line, and it's going to be a vector. You have to learn a vector, so we'll discuss this with linear algebra, and that will allow us to take this simple perceptron, which all of you will understand, and turn it into these kernels and SVMs, which are going to give you these models which are maybe more curvy. Okay? If I don't want to learn a straight line, but I want to learn a curvy line, how should I do this instead? And it turns out the same perceptron algorithm can be used here. Either you can use perceptron, or I can use gradient descent. Okay, I can write this down as an optimization problem and use gradient descent as well, and that's more common. We'll learn not just gradient descent, but the version of it like stochastic gradient descent, which is not much harder, but is what's used for these large these things for large data. Where okay, so you're gonna learn all the pieces, and you're gonna learn the mathematical notation for how to discuss this and to easily understand what's going on. Okay. Hopefully it's easy, right? So the goal of it is to introduce this at a gradual pace where this notation, which if you looked at it right now, if you looked at the last chapters in the book now, they're going to look like what's going on. By the end, there's going to be natural and easy as, yes, clearly that's the right way, the simplest way to think about this and understand it. Yeah.
So there are other methods where once you cluster them, you already have a classification? Because like, let's say you're clustering something, right? You're like trying to like, it comes out with like species, right?
Yeah.
And then you add a new species into that data set. Is there other methods that are better fitted to then classify that new entry?
Yeah, so that's a good question, but the answer is kind of like actually the last thing I want to talk about is how these all fit together. They're all related, and they can kind of be used. One, like clustering could be used for classification, regression could be used for classification in certain ways, but they're solving different kind of fundamentally different problems in certain ways. And let me draw a diagram to try and explain this. I'll leave it right in the middle here. So, okay, so let me just make sure I get good nomenclature. Okay, so okay, so I'm either going to have labeled data or unlabeled data, and I'm either going to and either this is going to be a set-based data, or it's going to be value. Okay, and there's going to be 4 squares here. And so if I have unlabeled data and I want the output to be a set, right, then this is going to be clustering. Okay, so I just had data points come in, and the output is it's in one of these 3 sets. Whereas classification, I have labeled data. I have the pluses and classification. I have labeled data, and the output is a set. I have extra information here. The input, the stuff I'm training on to build my model, the data points are pluses or are these minuses. Okay? And so I want the sets to respect that. Now it could be, there could be this other example here where, where I'm going to have data that looks like okay, so I have labels on these data, and it looks like, well, there are 3 kind of clusters of points here, but really what I want is a classifier that does this. I want to separate the positives from the negatives here. It doesn't matter that these are close to each other and these are close to each other. I still want to separate them because the labels are different. The fact that I've been given this labels, I need to respect them with the classifier. Where the clustering doesn't know anything about these labels. Okay? And then, similarly, if it's a value instead, I don't have a set outcome, I have a value outcome. Then if I have labeled data, the value here is the weight. Okay, I'm trying to predict this weight value here, so this is going to be, so this one is going to be regression. Right, if I don't have I'm not trying to predict a value here, I'm not trying to predict the weight, then this one is going to be just dimensionality reduction. I'm just trying to fit another kind of value based on mapping everything onto the lower dimensional subspace, but I don't have an actual prediction goal. I don't have the label of the weight I'm trying to predict. Okay, and so these are kind of 4 different kind of classes of these algorithms. And so you're right, if I did know the clusters and this really was the right solution here and I got another species coming in, then I would want to build another class. And if I didn't know the labels, but I kind of trusted these are the right, and I want to use this for classification, I could do that. But typically when we study the classification problem, we're given the labels ahead of time and we do prediction based. Okay, and this is, okay, so this class and this kind of personifies kind of the basics of what we teach in machine learning and data mining class. They get into more stuff like graphs and other sort of issues. This is not all of data analysis either, right? We've kind of given you, this is a nice kind of breakdown of what's going on. The nice thing about this is we'll be able to think of all this stuff really accurately through a linear algebra representation of it. If you're thinking of your data as a graph like you're dealing with like a social network, the structure changes. Okay, sometimes there's a lot of stuff that carries over, like the eigenvalues are still really important when dealing with graphs. If you're dealing with an AI instead of machine learning, one of the differences in AI is as you're collecting and building model, the environment is changing. So AI is kind of, think of it as more general than machine learning. Machine learning is the static case. There is data, and the data is fixed, and there's new data, and it looks just like the old data. Generally, that's kind of what you think about. With AI, think of like a robot moving through, and maybe you're interacting with the environment. A self-driving car may cause other cars to move in certain ways, and that changes what things look like. Machine learning is a nice, and classification is a nice, useful tool. Clustering is a tool as part of that, but there are other aspects than just this kind of 2x2 matrix of what's going on here. There are other ways of dealing with this through like visualization as another kind of channel for dealing with this, which brings a lot of different things to the table towards this, and isn't precisely one of these things, but is a tool that is part of the data analysis process. Okay, so this class isn't everything. It's leading to very directly to the data mining machine learning class, where we teach a lot more of this, the AI class, the visualization class. There's whole other directions that are doing a lot of cool stuff. But I think if you take this class, there's a lot of, it'll be at a good pace. You'll learn a lot of mathematics. I'll prepare you to kind of understand this kind of new, not totally new, but newish for me kind of world. So. Okay, great. So we'll start with probability review on Wednesday. We'll see you all then.